Mansur sir.
Hello, sir.
Sir, please allow me to share my PPT.
Okay. The thing is that only three participants are there, including me, you, and one more participant. So let's wait for some more time.
Yes, sir. During the time, I will show the first slide, then the people will start.
Okay, fine.
Security. Sir, ഇപ്പൊ ഒന്ന് try ചെയ്ത് നോക്കൂ.
Sir, is the PPT visible, sir? Sir, is the PPT visible?
Yes. PPT is visible.
Hello, sir.
Yes, sir.
Let's start the count. Count attain 60.
Sorry. Okay, sir. Okay, sir.
Okay, let's start. So, Tasneema will introduce you.
Good morning, everyone. So today we have Dr. Mubarak Ali sir. He's working as assistant professor in Department of Mechanical Engineering, TKM College of Engineering. He took his PhD from Nanyang Technological University, Singapore, in Mechanical and Aerospace Engineering. And he took his MS from IIT Madras and his graduation BTech from Madras Institute of Technology, Anna University, Chennai. And his research interests include novel composites design and manufacturing, surface modification, development of new composition from waste, impact damage of composite laminates, data analytics, design of experiments. And he has several publications in SE and Scopus indexed journals, and several book chapters are written. Book chapters are written by him, and he is a peer reviewer in several international journals and also a member in Indian Institute of Metals and the International Association of Engineers, Royal Statistical Society, etc. And he has delivered several keynote addresses and expert lectures in different areas. And today we have Dr. Mubarak Ali sir with us. So over to you, sir.
Thank you very much for the kind introduction. Is my voice audible? Is my voice audible, or should I increase my voice?
Yes, you are audible, sir.
Okay. So, welcome all to this session on data-driven modeling. Good morning, one and all. So what we are going to see in this session is how we can do some modeling based on the data. So I am going to introduce you to some interesting modeling levels. That is 3 levels of modeling: white box modeling, gray box modeling, black box modeling. So here I am going to use simple examples to explain you about white box modeling, gray box modeling, and black box modeling. And then in black box modeling, I am going to explain how this simple linear regression modeling, multiple linear regression modeling, polynomial nonlinear regression modeling, how these modeling are used. I'm going to give some simple theories which is required to understand this linear and non-linear regression modeling. Based on that, I'm going to use the data set which Mansur sir has shared in the group to demonstrate how the data is used to do some modeling of the process of the situation using black box modeling. So let us go to 3 classes of systems. People, researchers have defined 3 classes of systems. They are white box systems, gray box systems, and black box systems. That is, in white box system, all necessary information is completely available, completely known. So that means we know everything about the system. That means every data or every relationship is available. We understand the relationship between different parameters that is controlling the system, the parameters that is controlling the system. That is white box modeling. So there is something called black box modeling, where you don't know anything about the relationship existing in the system. That means relationship between the input and output parameters, or relationship between the factors which is affecting this system. And there is something called gray box modeling. In gray box modeling, we will have, is my pointer visible? Just now I introduced my pointer. Is it my pointer, red color pointer visible?
Yes, sir.
Okay. So this is gray box modeling, where we know only partial information. The remaining part is unknown. Only some part of the relationship we know, some parts we don't know. So there are three systems: white box, gray box, and black box systems. Depending upon that, three levels of modelings are there. That is white box modeling, gray box modeling, and black box modeling approaches. Three different approaches are there. In white box modeling approach, we will have we know every first principle. That means we know the physical laws, mechanical laws, chemical laws, which are actually explaining the system, or different relationship existing in the system, or the relationship between different factors, different parameters existing in the system. That is white box modeling approach. In gray box, we know the first principle. We use first principles, that is some of the relationship are known as well as some of the relationship are unknown. So those known relationship are called first principles, and these unknown relationship are actually modeled by this data driven modeling technique. That is gray box modeling. In black box modeling, we don't know anything about the first principle. That means we don't know any physical laws existing in the system, mechanical laws or chemical laws existing in the system. So it is completely data driven modeling in black box modeling approach. That means let the data speak for themselves. We don't have any prior information about any kind of relationship in the system. So if we compare these three modeling approaches, this is black box, this is white box, and this is gray box. In black box, we don't know anything. So here, the model, the level of available physical knowledge about the model, the level of model available, the level of physical knowledge available of the model is very, very less. That means near zero. So that is black box modeling. Here we know everything. So that is white box modeling. That is the level of transparency. There is a lot of transparency in white box modeling. In black box modeling, there is no transparency. That means we don't know anything about the system. So we have to, no other way, we have to completely depend upon the data from these black box systems to use that data in black box modeling to find some relationship which is existing in the system. So let us take some example of white box modeling first. This is a very good example, very simple, because I have taken some simple examples so that you understand and appreciate this different modeling techniques. This is the first. This is called first equation of motion. We have studied in static dynamics or engineering mechanics. That is V equal to U plus AT. What is U? U is the initial velocity. V is the final velocity. A is the acceleration. T is the time. So if we know the initial velocity, and if you of an object, and you know the acceleration of the object, and you know how much time it has taken to travel some distance, then you can find out the final velocity of the object based on this equation. This equation is derived using some first principles. Okay, so some laws are used, and finally we have derived this equation in our schools maybe, or in our first year of engineering maybe. So that is our relationship between final velocity and time, provided acceleration is constant here. Provided acceleration is constant here. And this A acceleration is a constant, means that is also called assumption. Acceleration is constant, that is assumption. If the acceleration is changing continuously, then we cannot use this equation. We'll have to use a different equation, which partial differential equation and all. So that will be a different equation altogether. So with a simple assumption called acceleration constant, given the time and the initial velocity, you can find the final velocity based on the physical laws, existing physical laws, and this is called first equation of motion. It is widely used everywhere, and we still use this equation. So here, the objective of this is a model, right? This is a model. What is a model? Actually, people think modeling in a very complex way. Actually, very simple explanation of modeling is relationship between two variables is called modeling. If you are able to express this relationship in a form of a numerical equation or in a form of any equation, that is called model. So here, this is a model which explains the relationship between final velocity and time, provided acceleration is constant. That is, assumption is acceleration is constant. In every model, there will be some set of assumptions will be there. One assumption will be there at least. There may be multiple assumptions. So this is a very simple model. This is another model. This first equation of motion. This second equation of motion. This is also giving the relationship between displacement and time. This is giving relationship between velocity and time. This is about the relationship between displacement and time. S equal to ut plus half at square. Provided here also acceleration is constant and you know the initial velocity. So when you know the initial velocity and acceleration is constant and you know the acceleration also, so you can find out the relationship between displacement and time using this model, the simple model. So these two models, everything about the velocity in the first model, this model, you take this. Everything about the velocity and time, that is the relationship, everything about the relationship between velocity and time is fully known. So we are able to establish this model based on physical laws. Okay. This is a relationship between displacement and time, completely defined. The relationship is completely defined. So nothing is hidden here. Nothing is hidden. Nothing is, unknown here. Only some assumptions are there. Okay. So this is about a very good example of white box modeling. Now another white box modeling is Ohm's. We can write Ohm's law, I equal to V by R. So this you people are even more convenient than me in Ohm's law, because you are from electrical background, electronics background. So here, what is this Ohm's law? Ohm's law defines the relationship between current and voltage. Okay. The current through a conductor between 2 points is directly proportional to voltage across 2 points. So that is written as I is directly proportional to V. So the I is V by R. R is a resistant and R is a constant here. Okay, R is a resistant, is a constant here. And this relationship between I and V can be explained by this figure, because people understand pictorial representation better than equational mathematical representation. So now if you see, this guy is the current ampere. So this amp fellow is trying to cross this. This is trying to move. Okay. And this voltage, this fellow voltage is trying to push this fellow as far as possible. Okay. So your current is dependent upon the voltage. That means the voltage pushes more, the current travel, the velocity of the current will be more. That means ampere will be more. But this fellow is a Ohm. This is a resistant fellow. This fellow try to resist the motion. As far as possible, he will try to resist the motion. So if resistance is more, current will be less. If voltage is more, current will be more. So that is the relationship between current and voltage with the constant resistance. And this fellow is applying this constant resistance. So very a funny as well as a pictorial, very good pictorial representation of the relationship between these three fellows, that is ampere, volt, and ohm. So here also, you know completely the relationship between current and voltage here. So this is white box model. Very simple equation with the white box explaining white box model. Now in this same case, if resistant is not constant, for example, resistant keep on changing. So what will be the relationship between I and V? You understand it is not simple. This Ohm's law will not be applied there. So you will have a very complex equation, different equation with the complex formulas. So depends upon the assumption your white box model, numerical model will be changing. Now there are some more. I want to give some example of white box modeling where you get complex relationship. This is equivalent flow stress applied in terms of principal stress. So this is the equivalent flow stress. If you know sigma 1, sigma 2, and sigma 3, that is principal stresses. This is from engineering mechanics. Another equation is the radius of crust zone. If suppose if you throw a stone on a wall, okay, or you fire a bullet on a wall. So what will be the radius of the crushed zone? The wall will be crushed at one point, small region, small diameter. So what will be the radius of the crushed zone? And the relationship between the radius of the crushed zone and the initial radius is given by this RC by R naught. This is a formula. So you can see three complex equations are available. These are all white box modeling. That means what is white box modeling? The complete relationship between the two factors or two unknowns are completely known. Nothing is hidden. Everything we know. So that is white box modeling. Now come to gray box modeling. Here in gray box modeling, only half of the partial information about the physical laws or the physiological knowledge about the system is known. Physical laws are there, but it is not completely defining the relationship. So to understand complete relationship, you need data-driven modeling as well as data-driven modeling approach and equations using data available from the system to completely define the relationship. So only partial relationship is known. So that is gray box modeling approach. Let us take an example of this. Let us take a simple example to try to understand what does it mean by gray box modeling. The amount of this is a spring. This is a spring, okay, which is hanged from this top part. Now you have a small box, a small weight here. This weight is hanged at the bottom of the spring. So what will happen? Depending upon the weight, the spring will go down. If the weight is more, spring will go more. If the weight is less, spring will go less. Okay. So depending upon the weight, the elongation of the spring, that is the amount of force applied to elastic object, that is the weight is the amount of force applied. So you can convert weight into the force. Amount of force applied is directly proportional to how far it stretches. That is, your stretching of this spring depends upon this weight. That is the information you know from Hooke's law. That is called Hooke's law. That is the information we know. But actually, how much is the amount of how much is the exact deformation or the elongation of the spring, we don't know. We can only write this Hooke's law. From this Hooke's law, we can write an equation like this: L equal to A plus B F. F is the force. F is the force means a weight. Weight converted into force. But A and B are unknown. This is the equation relationship between L and F. That is, L is the elongation of the spring. F is the weight of the object that is hanged, that is attached to this spring. So we can write from this Hooke's law is a physical law. So physical law, from this physical law, we are writing L equal to A plus BF. Now what is A and what is B, we don't know. So unless we measure, unless we take some data from the equation and try to find out A and B, we will not be able to know A and B. Unless A and B are known, then unless it is known, we cannot say it is a complete relationship. So only partial relationship we are having. Unknown parameters are there. So we have to find A and B now. So how do you find? Take data from this experiment. Okay, take data from this experiment. Take data at point A. Okay. Apply force. The spring has elongated up to point A. Apply a lower force. Spring has elongated up to point A here. So note down the force and length. Apply increase the force. Spring has elongated up to B. So you write note down the force and the length. Apply even more force. So keep on applying. 7 times you apply different forces and measure the length. So this is the data, experimental data. If you draw this experimental data here, so almost there is a straight line. So you can fit a straight line conveniently. At least from A to E, there is a straight line here. So there is a small curve there. So let us make an approximate straight line equation. Okay. So this is an equation of a straight line. So now using this data, we can find the unknown constant that is called A and B. So that is found from this data that L equal to 1.2 plus 0.44 F. So now using the data as well as the Hooke's law, that is a physical law, we are able to find the complete equation, which is L equal to 1.2 plus 0.44 F. Okay. So that is the complete equation is available. So partially some information is taken from Hooke's law, partially some of the unknowns are calculated from the experimental data. So that is called gray box modeling. So come to black box modeling. Here you don't know anything about the physical laws. That means you don't know anything about the relationship existing in the system with the physical laws or chemical laws or whatever it is. So only data you can generate from the system. So from the data, we have to do some modeling. For example, let us say this black box name has come from what is the meaning of black box. Let us understand. Nothing of the true system is known or can be known. That is the meaning of black box. That means you don't know anything about something, then we say that is black. Okay. People from the Western countries, they use black word if they don't know anything about something. Okay. So what is available are recorded are only the recorded data of the system of interest. For example, people say dark matter. How many of you heard this name? Dark matter. Dark matter, dark energy. Our universe. You see this energy distribution of this universe. Our universe is almost 69% dark energy and 26% dark matter. And known matter, matter, universe is made of matter. So known matter is only 5%, unknown matter is 26%, unknown dark energy is 69%. So almost total 95% of the universe is unknown. That means you don't know anything about it. You only know 5% of this universe. That is 5% is the normal matter. So only you can get the information. Because you can try to understand only this 5%. Even in that 5%, people don't know anything, everything, 100% of this 5%. People are still trying to find out new things in this 5% of the normal matter. So finally, we don't know, we know only very less about this universe. Most of the universe is actually composed of dark energy and dark matter. That is why they are mentioning the scientists used to call it as dark matter, which means we don't know anything about this matter. Only information we know about this dark matter is, this dark matter is not similar to the normal matter. This is the only information we know. Dark matter is not similar to normal matter. That is the only information we know. It's completely different from normal matter. So that's why they have named us dark matter. Dark energy, they say dark energy is not similar to, normal energy. Only information about dark energy is this much. So rest of this is dark energy. Now black box modeling, normally people use different kind of techniques to understand or to generate data from black box modeling and try to find out some relationship existing in black box. For example, in a trial and error process is used, you can estimate the parameter various structures and compare the results. So generally people go for trial and error process. Also, that is the data that we can do is let the data speak for themselves. You don't try to explain anything. Let the data speak for themselves. Okay. Let the data speak for themselves. You don't do anything to change anything. You take whatever data available, try to understand things from the data and try to model it. That is black box model. Here, different kind of techniques are used. Linear, non-linear models. Different kind of model classes are linear, non-linear, parametric, non-parametric, continuous, discrete, lumped and distributed models. Different type of model types are regression, differential equations, difference equations, artificial neural networks, statistical models. So here I am going to explain you about some regression model. How using this regression model, we are able to generate some relationship existing in black box systems. So here, let us say this is the input signal. Okay, after processing, you find this is the output signal. Okay, this is the input signal, this is the output signal. So what is the relationship between the input and output? That we don't know. Okay, that we can find from this data. That we don't know, we can find from the data. But actual true system model structure is not known. We don't know about the true system model. So only we have input and output signal. So what we can do is from the input and output, we can try to find out how, what are all the unknown relationships between input and output that will give some information about the system. Okay. So any doubts until now? Because I have given a brief introduction about white box, black box, and gray box modeling. Anybody want to ask anything? Any doubts or any clarification required? Okay. So I'll go to the next topic, which is actually simple linear regression modeling. Why I am trying to give some theory of the simple linear regression modeling. See, there are a lot of softwares available for regression model. What happens is if you give the data, the software will give the model. But how does this data is processed? How the relationship is actually calculated? Unless you know about it, how are you going to use this numerical model? Simply you give the data and get the model from or the statistical model or the numerical model from, that is the model, statistical model or regression model from the software. We will not be able to understand fully how we are getting this model and what exactly this relationship is trying to convey. So for that we need to understand how the simple linear regression modeling is done. Okay, for example, let us say these are the simple linear models. This is salary of people. This is the year of experience. That means salary. What is the relationship that exists between years of relationship and salary? So that's what somebody want to study. So he collected some data. So somebody with 1 year, half a year, 1 year experience, and somebody with the 10-year experience is there. He just plotted. He plotted with X and Y axis. Then this red color line you can join very conveniently. You can join, and try to say there is a relationship between years of experience and salary. And that relationship is actually given by this red color line. Okay. So that is a simple linear line actually. Similarly, somebody wanted to calculate the latitude and the mortality rate of skin cancer patient. So if the latitude is very high, the mortality rate is low. If the latitude is lower, the mortality rates are higher. So here we can find that there is a linear relationship existing, but it is in a negative linear relationship. So positive relationship, this is negative relationship between latitude and mortality. So all these things we can get from a scatter plot also. We can see what type of relationship exists. So how do you get the actual equation? There is an equation here. Y cap equal to 389.2 minus 5.98 x. So how do we get this actual relationship? That I am going to explain you now. So this is some examples of linear model. This is some examples of nonlinear model. This nonlinear models, you can have various nonlinear model. This is exponential model, logarithmic model, power model, polynomial model. So we will see how we are going to get this polynomial or nonlinear models also from the existing data of the black box systems. In the last part, we are going to see how we are going to do nonlinear model. So here, simple linear regression model. Here, the statistical this statistical modeling technique explores the relationship between two or more variables. So at least two variables should be there, or more variables can also be there. In simple linear regression model, you will have one dependent variable and one independent variable. That is called simple linear regression model. If you have only one dependent variable or one independent variable, then we call it as simple linear regression model. What is dependent and what is independent variable? Anybody know what is dependent and what is independent variable? If anybody know that, please tell me. Okay. Dependent variable means if you write y equal to a plus bx, then y is dependent on x. X is not dependent on y. X is independent. So y is the dependent variable. X is the independent variable. That means x does not depend on y, but y depend on x. So let us take an example of this chemical distillation process. Here oxygen is produced, and this oxygen, the purity of oxygen is represented by y. Purity of this oxygen depends upon hydrocarbon level. Let us say we are trying to find out whether this purity of this oxygen is depend upon this hydrocarbon level. So y depends upon x. That is, as per our assumption, purity of oxygen y is depends upon x, which is hydrocarbon level. But hydrocarbon level doesn't depend upon purity of the oxygen, because purity of oxygen comes in the later stage. In the initial stage itself, in the distillation process, we set the hydrocarbon level. So purity depends upon hydrocarbon level, but hydrocarbon level X does not depend upon purity. So that is why purity is called dependent variable. That is, Y is generally the dependent variable. All other remaining X are independent variable. Now you take this data. Some engineer has conducted an experiment in the chemical distillation process, and he has produced a lot of he generated data. So 0.99, all this data are there. So X and Y data he has calculated. X and Y data he has calculated. Now based on this data, what is going to happen is what are we going to do is we are trying to find out the relationship between Y and X, that is the purity of oxygen produced from the distillation process to the hydrocarbon level. Okay, first let us draw the scatter diagram. So you can see this is a scatter diagram, and hydrocarbon level is in x-axis, purity that is in y-axis. So we can see there is some relationship exists between x and y. That is some kind of linear relationship exists between x and y. So what we are going to do is we are going to say y is having a linear relationship, that is it is written as y equal to beta naught plus beta 1 x plus epsilon. What is this? X is the independent variable, y is the dependent variable. Beta naught and beta 1 are unknown coefficients. That is called regression coefficient. Epsilon is the error term. Why do we need epsilon? That I am going to explain you now. For example, if you draw a straight line, try to fit a straight line here. All these points are not falling on the straight line. There is some deviation from the actual point from the straight line. Okay, so that deviation is expressed in terms of epsilon. Straight line is expressed by these two terms, beta naught and beta 1x. So now if you see here, this is the data set, oxygen purity data. So from this data set can be written in a generalized form. Y is y1, y2, y3 up to yn, x, x1, x2, x3 up to xn. So there are n number of observations. That is, here in this example, 20 is the n equal to 20. There are 20 different observations in this data set. Now, we have this equation, y equal to beta naught plus beta 1x plus epsilon. Now we are going to use this equation. We are trying to fit this equation. So we are writing that y1, using this 20 different equation, we can write y1 equal to beta naught plus beta 1 x1 plus epsilon 1. y2 equal to beta naught plus beta 1 x2 plus epsilon 2. y3 equal to beta naught plus beta 1 x3 plus epsilon 3. Similarly, last observation, yn equal to beta naught plus beta 1 xn plus epsilon n. So 20 different equations are there. If you are able to write this 20 different equation into one matrix form, we can write y equal to x beta plus epsilon. Y is the matrix, x is a matrix, beta is also matrix, epsilon is also matrix. Okay, that matrix representation is given by this. Y is a column matrix, y1, y2, y3 up to yn. X is also a matrix, that is y into n matrix, that is 1, 1, 1, 1, 1 in the first column. In second column, all the x values are written here. Beta is a column matrix with beta naught and beta 1, because in this original equation, we have only beta 1, beta naught and beta 1 as the unknown coefficient. Epsilon is epsilon 1, epsilon 2, epsilon 3 up to epsilon n. Okay. So this equation can be written in one single matrix form, that is y equal to x beta plus epsilon. Now, using method of least squares, we can find what is the sum of square of the deviation of each point, because the points are not going to lie in the straight line. So find out the sum of the square of the deviation. Because why I am finding sum of square of the deviation, I can simply find sum of the total sum of the deviation, adding all the deviation. But what happens is some of the deviations are positive, some of the deviations are negative. So it may get cancelled out. Sometimes you will get 0, some of the deviation. So in order to get all positive values, we are finding sum of the square of the deviation, that is sigma epsilon I square. Epsilon I is the deviation. Sigma epsilon I square, I am writing it as L. L is the sum of the square of deviation. Sigma epsilon I square. So try to find this. Then I am trying to minimize this sum of the square of the deviation. How do you minimize something? Differentiate it and make it equal to 0. So differentiate L with respect to beta naught, make it equal to 0. Differentiate L with respect to beta 1, make it equal to 0. Rearrange the terms, you get two different equations like this. The equations are called least square normal equations. We can write these least square normal equations in matrix form. That is x transpose x beta is equal to x transpose y. So this is the final least square equations in matrix form. If you are, this is the equation which we are going to use in this regression. All kinds of regression equation is solved by this one simple regression matrix equation, which is x transpose x beta cap equal to x transpose y. and beta cap is the unknown. We know x, so from x we can calculate x transpose. We know y. So using this, we can find out x transpose x. We can find out x transpose y. So only beta is the unknown term. We are supposed to find this beta now. So beta can be found out by x transpose x inverse x transpose y. Okay. Now what is x? What is x? X is given by this matrix. This is x matrix. This is y matrix. This is beta matrix, and this is epsilon matrix. Here to calculate beta, epsilon is not required. Okay. So this is the equation of least square in matrix form, and this equation is used in finding all the regression coefficients. And this is very versatile equation. Just to remember this equation, we can find every software is going to calculate this equation, going to calculate this equation and find out beta naught from this and try to give the output. Okay, for example, let us see the same oxygen purity data, fit a regression model. How do you fit a regression model? Find out x, sigma xi, sigma yi, x bar, sigma yi square, sigma xi square, sigma xi yi from this data manually. Then find out beta from this equation. Sigma from this equation. From this equation, try to find out beta. Now beta is actually beta naught is 74.283 plus 14.947. That is beta naught. Beta 1 is 14.947. Okay, so we have found this beta and beta naught using the equations given in the previous slide. So software also uses the same equation and try to find beta and beta naught, beta 1 and beta naught. Okay, now given the point estimate of oxygen purity, when give a point estimate of oxygen purity when hydrocarbon level is 2%. In this, you see hydrocarbon level is never 2%. The maximum hydrocarbon level is 1.55. So if, for example, if I set hydrocarbon level at 2%, what will be the estimate of oxygen purity? What will be the approximate oxygen purity? Try to estimate. That is the question. So substitute x as a 2.0, you get y, which is 104.177. Okay. So x at y at x equal to 2, y at x equal to 2.0 is 74.283 plus 14.947 multiplied by 2 is 104.177. That is called predictive analytics. That means you use the existing relationship y equal to 74.283 plus 14.947x and find out the value of y at x is equal to 2. That is called predictive analytics. Okay, this is diagnostic analysis. The finding out the existing relationship is called diagnostic analysis, and finding out this y at x equal to 2 is called predictive analytics. One more problem. In an ultrachemical machining process, a data is taken. What is the people are trying to find, took a data from the experiment. X is the gap between the tool and workpiece. Y is the amount of metal removed in the electrochemical machining process in grams. So they have got this data, simple data. So from this data, we can find that using the matrix equation, y cap equal to 7.6 plus 4.2x. So this is an exact relationship between x and y, not an exact. Is a statistical relationship, regression equation or regression relationship between x and y. So somewhat we are able to know what is the exact relationship, what is the relationship that exists between x and y. So unknown, it is known now. Earlier it was unknown. From the data we are able to find. Not from any physical data, it is from the statistical data. Now there is something called error term in the equation, epsilon I. So why are we going to use this error term? Actually, this error term is used to find R square value, which is called a coefficient of determination. Now, how do you find R square value? Find out sigma I square, sigma epsilon I square, that is L. L is the sum of the square of the deviation. So sum of the square of the deviation is sigma epsilon I square. So that you will get as SSE, that is called the sum of the square of the deviations. Sum of the square of the deviation, SSE. And sum of the square of total, sum of the square of total is sigma yi square. Take y column, that is sigma, that is add y1 square plus y2 square plus y3 square up to yn square, you get sigma yi square, that is SST. So using this SSE and SST, we can find R square, that is coefficient of determination, is 1 minus SSE by SST, that is called coefficient of determination. What is the significance of this R square value? It quantifies the model closeness to the data. That is, how does this model is closer to the data? That means how this model is explaining the relationship, that is how this model is explaining the relationship existing in the data, how close this model is actually explaining the data, is representing the data. That is, it quantifies the model closeness to the data. So if R square value is high, your model is very good. If R square value is lower, your model is not very good. It's not good. So you always try to get higher R square value. So if R square is 1, it is a perfectly, the data, the line, that is the line perfectly fits the data. And if R square is 0, the line does not fit the data at all. So for this oxygen purity regression model that we have calculated in the previous slide, previous 2 slides, so we are able to find R sigma SSE and SST. SSE is 29.26, SST is 173.737. So you get 0.877, that is 87.7% R square value. That is 0.877 R square value, which is very good. Any R square value greater than 0.85 is a good R square value. Okay, it's a very good R square value. Now, it will never happen that the regression line perfectly fits the data. So you will never get R square equal to 1. Also, you will never get R square equal to 0, because there will be some information relationship existing between the 2 variables. So you will never get R square equal to 1. R square equal to 0 also. Now let us understand the meaning of R square value. If you see here, this is a strong R square value plus a positive R value. Positive relationship between X and Y, and this is a strong R value, and this is a negative relationship, strong, because why it is strong? Because the points are closer to the line. That is why strong R square value, that is higher R square value, and positive, because when X increases, Y also increases, it is positive. Here strong negative relationship, that means minus R will be negative but higher value, because the points are closer to R, but closer to the line. Here it is a weak positive R square value, that means the points are away from the line compared to this. This is a weak negative R square value, that is points are away but it is a negative relationship. So this is how we try to interpret the meaning of R square value in simple linear regression. That is, R square value quantifies the model closeness to the data. Now some more examples of meaning of R square value. Here you see the R square value is 0.297. Here you see 0.312. Here it is 0.482. This is 0.483, 0.308. This is 0.047. Okay, that means 0.047 means nearly 0. So there is no, if you fit for this data, if you fit a straight line like this, it's not at all, points are very much far away from this straight line, so not fitting properly. So R square value is 0.047. That is the theoretical aspect of simple linear regression model. So now with the same concept, let us explain something about multiple linear regression modeling. In multiple linear regression modeling, this is a simple linear regression model. Let us take again the same example, simple linear regression model. In simple linear regression model, only one predictor or regressor available. That is only one x variable, only one y variable, only one x variable. Okay, only one x variable. So we can write an equation of a straight line. But in multiple linear regression, you get more than two regressive variable or predictor variable, more than two variable. That is more than one x variable. So here we will represent x as x1 and x2, x3, x4, x3 like that, xk up to x k number of x variables will be there. So how are you going to deal? Because when there are more than more than one x variable, the situation is getting complex, right? That means a lot of parameters are playing around. So how are you going to model it? So what is the approach we are going to see? For example, let us take this example, that is your gasoline mileage depends upon, that is your vehicle mileage depends upon two things. Let us say two factors are affecting your gasoline mileage, that is vehicle weight and engine displacement. Normally, if the weight is more, your mileage will be less. If the weight is less, mileage will be more. And engine displacement, if the engine displacement is more, your gasoline mileage will be more. If the engine displacement is less, mileage will be less. So that we get from the data that we already have it in our mind. But initially, people doesn't know what is the exact relationship between weight, displacement, and gasoline mileage. So people thought, let us take this data and represent it by a multiple linear regression model. It is y equal to beta naught plus beta 1 x1 plus beta 2 x2 plus epsilon. Here y represent mileage, x1 represent weight, x2 represent engine displacement, sigma represent random error term. The above equation is a linear function. Okay, the above equation is a simple linear function. But the two x variables are there, x1 and x2. Okay. Now, how do you represent? Because if there is one x1 variable, you can represent with the form of a straight line. Now, when there are two x1 variables, for example, this is your multiple linear regression model, y equal to 50 plus 10 x1 plus 10 x2. How do you represent? Represent with the equation of a plane, equation of a straight plane. So this is an equation of a straight plane. Beta is the intercept of the plane, that is, this is the beta, where this plane intercept to the y-axis, that is the beta. Beta 1 is the expected change in the y per unit change in x1 when x2 is held constant. Keep x2 constant. Change x1 1 unit and find out what is the change in y. That is beta 1. Similarly, keep x1 constant. Change 1 unit in x2. Find out what is the expected change in y. So that will be the beta 2. Now in multiple linear regression model, there may be more than one x variables. So you can have up to xk variables, that is x1, x2, x3, x4, x3, x5, up to xk. So same method is used, that is the same matrix method is used, same formulas are used, but that is the least square method is used to find out the relationship existing between x1, x2, x3, xk and y in multiple linear regression equation. So there is something called a cubic polynomial model, that is a nonlinear model. Same model can be represented, same matrix equations can be used to find out the relationship in a nonlinear model that we will see in the end. Now, there are something called a regression interaction effect in multiple linear regression. That is a nonlinear regression. There is something called nonlinear regression. For example, if you write an equation like this, y equal to beta naught plus beta 1 x1 plus beta 2 x2 plus beta 1 2 x1 x2. What is this? Beta 1 2 x1 x2. This is a linear term. Beta 1 x1 is a linear term. Beta 2 x2 is a linear term. Beta 1 2 x1 x2 is a non-linear term, because this is actually introducing nonlinear term, because the order of this term is 2. It is x1 and x2. Total order is 2. Here only one order. Order is 1. Here also only one order. Here two orders are there. So because of this, this is called interaction effect. Interaction effect, this x1, x2 is called interaction effect. How this two effects, x1 individual effect, main effect, x2 main effect, combine together and influence y. That is called interaction effect. So let us say this is an equation with an interaction effect y equal to 50 plus 10 x1 plus 7 x2 plus 5 x1 x2. This is an interaction effect. This is main effect of x2. This is main effect of x1. So you see the plane is twisted, somehow twisted. So non-linear plane. It's not a linear plane. So non-linear plane, the twisting is actually given by this 5x1 x2 term. Because of this 5x1 x2, there is some twisting in the plane. Now you take this equation. Here you have interaction effect of 4x1 x2. This is quadratic effect 5x1 square. This is quadratic effect 8.5 x1 square. Then you have linear effect 10x1. Another linear effect 7x2. So altogether you have linear term, quadratic nonlinear term, interaction effect nonlinear term. So three nonlinear term, two linear terms are there, totally making the model highly nonlinear. So that's why if you draw a plane for this equation, the plane looks like this. That is very, very bent and twisted. Twisting and bending are more. So that's why you see it's a curved plane. So this equation is represented by this curved plane. So you have why we are representing it a plane, because there are only two x variables. When there are two x variables, we can represent by a plane, either by a straight plane or curved plane or twisted and curved plane, whatever it is. But when there are more than two x variables, for example x1, x2, x3, then we cannot draw a plane, because plane needs only two x1 x variables, one y variables. So how do you draw a plane or some pictorial representation when there are more than two x variables? So that is an imaginary plane with the 3 degree, with the third degree imaginary curve with the 3 degrees, x1, x2, x3 and y. Okay. So that we are not able to draw it, we can only represent by a equation form. Okay. So here also method of least square is used. That is sigma epsilon I square is found out, and that is partially differentiated with respect to the unknown coefficients of regression, that is beta 1, beta 1 and beta 2. So you get three different equations. So three different equations are represented here. Minimum three equations. The maximum depends upon the number of x1 variables, x variables. Sometimes you get k number of x variables, x1, x2, x3 up to xk. So you will get k number of normal least square normal equations. That is k number of least square normal equations. These equations can be represented in the form of a matrix equation by drawing a matrix like this. If y equal to y1, y2, y3 column matrix up to yn, x equal to 1, x1, x11, x12 up to x1k. Then like this, if you write all the x data set, x1 in one column, x2 in another column, xk in a third column, the first column is written as 1, 1, 1, 1. Then that is called the X matrix. Then beta matrix is beta naught plus beta 1 plus beta k up to beta k. K number of, that is k plus 1 number of unknown variables. Epsilon matrix is epsilon 1, epsilon 2, epsilon 3 up to epsilon k. So total, if you write all the different terms, x, y, beta and epsilon in term of matrix, then we can represent a matrix equation like this, which is actually x bar x transpose x beta is equal to x transpose y. Okay, this is exactly representing these three least square normal equations. These least square normal equations are similar to the least square normal equations in simple linear regression models. This derivation and all is not at all required for you. Only thing is you can understand is these three equations we get from the method of least square criteria, which says that the sum of the square of the deviation should be minimum. So when we say something is minimum or maximum, So we can immediately say differentiate that equation and make it equal to 0. Then only we get a minimum or maximum. Minimum or maximum. So since sum of the square of the deviation should be minimum, so what we have to do is we have to differentiate that equation with respect to unknown coefficients beta naught, beta 1 and beta 2 and make it 0. So there are three equations, simultaneous equations, that is represented by these three simultaneous least square normal equation that can be represented by one such matrix equation, which is called x cap x beta equal to x cap y. Okay. Now look at this data. In a semiconductor manufacturing process, you prepare a wire bond. This wire bond, full strength of the wire bond depends upon. Maybe we don't know whether it is depends or not depend. We don't know. We are assuming the engineer suspects that it may be depend upon wire length and die height. So he has taken a data from manufacturing of semiconductor wire bond. Manufacture of wire bond, the semiconductor manufacturing process. He has written y equal to, he has taken y. This is a full strength, and this is wire length x1, and this is die height x2. So you have how many x variables? Two x variables. That is two independent variables and one dependent variable. That is, this dependent variable is dependent upon two independent variables. So we are able to find out all the different terms in the least square required in the least square normal equation, substitute it and try to get this find out beta naught, beta 1 and beta k, beta 2 from the least square normal equation. That is 2.26. We found beta naught equal to 2.26, then beta 1 equal to 2.74, then beta 2 equal to 0.012. That we have found out from this equation actually. This is the matrix equation. So only this equation is required hereafter. After this, cause all these can finally come to one single equation called this equation. Okay. So for this wire bond strength data, we have found that y cap equal to 2.26376 plus 2.7442 is 7 x1 plus 0.01235 x2. So we can find r square also. That is r square equal to SSE by SST. So in this equation, we can find r square value is equal to 0.9640. So we have found two things. One is the relationship, and another one is the r square value, which is the closeness of this model with the data. So we have found r square value 0.96. 0.96 is a very good r square, very good r square. So we can say the data clearly, the model clearly explains the data. Okay, model is very close to the data, and the model is explaining the relationship very closely. That is the meaning of r square value. Now, if you see this equation, the coefficient of x2 is very low, 0.0125. That is almost 1 by 90 or 95 times. You know, if you divide, you get this 0.0125. The coefficient is very low. That means x2 is contributing very less to y. X1 is contributing more to y. X2 is contributing very less to y. So what people have done is, people are trying to find out this adding die height to the model increases r square by very small amount. So what you can do is we can remove this x2 variable and find out a simple r square value, which is if you remove the regression, the x2 variable, find out the simple regression variable, simple linear regression with only x1 as the regression variable. We get a simple equation. R square of that equation is 0.9811. So there is an improvement in r square value, that is 0.0171 improvement in the r square value. So it depends upon us sometimes if we think x2 is very costly to take, so if x2 is contributing very less to the model, then we can remove x2 and make the model simplified and use the simplified model straight away. Direct calculation even technicians can do. So well, if you are not convenient with this what do you say, x2, that is die height. If this die height measurement is actually taking is consuming a lot of cost and energy, then you can remove this die height and increase the r square value 0.9811. Okay. Sometimes you may say you are not worried about the cost involved in it, but you need a very good model. Then you can include the r square value and find out r square. You can include the x2 variable also. Find out r square, which is r square equal to 0.9811. That is, in this r square equal to 0.9811, x1 and x2 both are included. But if r square, if we find a model with only x1 as the regressor variable, only x1, x2 we have eliminated. So we get an r square value which is 0.9640. There is an improvement in the r square value by adding x2 term into the model. So now whether you need to include x2 in the model or not include x2 in the model depends upon you. You have to decide, because if your measurement of x2 data is time consuming and it is taking a lot of money, then what you can do is you can remove x2 variable and you get satisfied with this r square value, which is r square equal to 0.964. But in some critical cases like spacecraft and all, aircraft and all, you need a higher closeness to the model, but you are willing to spend some more money in taking the data. So in that case, what we can do is we can add x2 and x1 in the model and make a better model that is called 0.9811. Okay. Now, people are not happy with this r square value for multiple linear regression. Simple linear regression, it is okay, because only one independent variable, only one independent variable. But multiple linear regression, there is some difficulty in using this r square value, because r square value never decrease when a regressor is added, and it can be difficult to judge whether the increase is telling us something useful about this new regressor. So it is preferable to use adjusted r square value. Adjusted r square value is actually represented by this formula, which is 1 minus MSE by MST. Instead of in r square, simply r square value, it is written as r square equal to 1 minus SSE by SST. What is the difference between SSE and SST? If you divide SSE by the its degree of coefficient, then we will get MSE. And if we divide SST by its degree of freedom, then we will get MST. So if we find the adjusted r square value of the full sum data, it is 0.979 for the multiple linear regression model. So what is the benefit of this r square value? It guards against overfitting, including regression that is not really useful, reduces r square value, and it is useful in comparing and evaluating competing regression models. So what I am suggesting you is, for simple linear regression model, be happy with r square value, simple r square value. For multiple linear regression model, go for multiple adjusted r square value. And there is something called polynomial model. For example, if you are trying to find whether there is some polynomial relationship is there or not. So how do you use a polynomial model? You can go for a polynomial modeling technique like this: y equal to beta naught plus beta 1 x plus beta 2 x square plus beta 3 x cube plus epsilon. This is a linear model. This is a linear effect. This is a nonlinear quadratic effect. This is a nonlinear cubic effect. So you have linear effect also, quadratic effect also, and you have a cubic effect also. So it is a nonlinear model because order of x is 3. So completely nonlinear model. So let us, to solve this problem, with the same equation that we have derived, that is a matrix equation. How we are going to do is, people have found a simple way. Put x1 equal to x, x2 equal to x square, x3 equal to x cube. So then it becomes y equal to beta 1 plus beta 1, x1 plus beta 2, x2 plus beta 3, x3. So if you substitute this three variables in this equation, you get a multiple linear regression model. Use this multiple linear regression model, solve this model, and try to find out the equation, and then later final step you convert that into substitute. Instead of x you substitute x1 you substitute x, instead of x2 you substitute x square, instead of x3 you substitute x cube in the final equation. Then you get a polynomial nonlinear regression model. For example, this is a polynomial model. A sandwich panels for interior aircraft is made for interior of the plane in a 1,500 ton truss. The manufacturing unit cost varies with the production lot. So the production lot size is given by X. Manufacturing cost in dollar is given by Y. So you can see the manufacturing cost changes with respect to X. So what is the actual relationship between X and Y? We are going to find now. So before finding now, they have drawn a graph called graph with the X in X-axis, lot size in the X-axis, the average cost per unit in the Y-axis. Now you see there is some amount of nonlinearity is there, some curvature is there. So that is called nonlinearity. So based on that, we can say it is actually a quadratic second order curve. So we can find out we can include the quadratic terms in the model and try to find out the unknown coefficients of this quadratic model. So polynomial model may be appropriate in this situation. Using the data, we can do the polynomial. First, convert that polynomial model into multiple linear regression model, and use this multiple linear regression model to solve as per the normal procedure. And after solving, you know what is the actual actual relationship between X and Y. Now, for a sake of example, I have given a data set here. Now you see MEDV, this is the last column. MEDV is the dependent variable. What is MEDV? Median value of owner occupied homes. That is a median value of owner occupied homes in real estate business. So people find the owner occupied homes value of the owner occupied, median value of the owner occupied home. So people find out these statistics in the residential zones and different areas. They collect this data. From the data, they try to find out what is the relationship between MEDV, that is median value of owner occupied homes, with all other factors. So what they have done was they have taken data of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 individual independent parameters and one dependent parameter is MEDV. So if you look at this, this is a multiple. We don't know this is what kind of equation will get, but very complex equation will get. This is a multiple linear regression data. Maybe we may get a polynomial equation also. Since the more number of X is available here, more than 2, we are not able to use it. We are not able to represent in the name of in the picture form. But obviously, we can use this data to find out the relationship between MEDV, that is Y, with all the X, that is 12 X's are there. So this is one such data. Okay, one such multiple regression data. So I come to the end of this theory session. So now after maybe a small break, we can have a online workshop using the data set that Mansoor sir has shared in the group. So we are going to use that data set, and we will try to find out, we'll try to solve some black box modeling, how we are able to use the data from the model system to find out the relationship existing between different variables in the system. Any doubts if you have, please ask me. If you have any doubts, you ask me, and we'll go to the next session. that is in the workshop section. Please install Minitab using the link provided by the Mansoor sir in your laptop, and be ready with the Minitab for the next session. So once you are ready, please tell me. Okay, if you have any doubt, please ask me. I have just given the introduction about white box, gray box, and black box, and examples about these different models. And also I have explained you simple linear regression model, multiple linear regression model, as well as polynomial regression model. All this model that I am going to do it in the workshop now, so that you understand using Minitab. Minitab is a general purpose database software, data processing software, statistical software. So since trial version is available, so I am going to explain things using the trial version of Minitab. Is it okay, sir? Mansur sir?
It's okay, sir. Minitab link is already shared to the group, WhatsApp group. Hope all of you.
Yesterday, Mansur sir has shared it in the group.
Yes, sir. Minitab.
So you have to register and give your email ID. You give your actual name, institute detail. Then through email you will get the link for downloading and installing the Minitab. So every one of you has to do it individually. Also, the data set that I'm going to use for the analysis is shared in the group. So you can take a printout of the data set or at least download and save it in your computer. So what shall we do? Shall we start? What time we'll start the workshop?
Sir, we can wait for 5 minutes.
Give 10 minutes time. Let them install the Minitab.
Okay. Then after 10 minutes, we can start.
Okay. So please remind me. Please call me. Do you have my number?
Okay, sir. I have your number.
Call me when everything ready. Okay.
Okay.
Thank you.
So all participants, please install and leave a message that when you have completed this installation.
Hope all of you have installed the Minitab and set up everything. Should we wait for anyone? Like, is there anyone haven't finished, completed the procedures? So let's start, sir. Seems everyone has installed it.
Okay, okay, okay. So this is the Minitab interface, and I'm going to use this data set. Okay, this is already shared. Data set is already shared. So slowly, I'll take simple data and try to explain the concept first, and I will explain the same thing with big data, the concept, complex and data with a lot of factors. So let us say I'm going to use this one. Okay. So I'm going to use the data set one, that is spring length data. So in this spring length data, what I am having is I am having force and length. Length is a dependent variable and force is independent variable. So in Minitab, what you shall write is I am just I'm just extending this workshop or this worksheet slightly bigger. In the first row, C1, just below C1, I am writing force. Okay. And just below C2, I am writing length. Because I am going to enter the data of force in this column, data of length in this column. I'm trying to now enter the data. 1.1, 1.9, 3.2, 4.4, 5.9, 7.4, 9.2. Okay. Now I am entering the length data 1.5, 2.1, 2.5, 3.3, 4.1, 4.6, 5.0. So please enter the data like this. Now I have entered the data set 1 as given in the same format as given in my data set. Okay. So data are entered like this in this Excel, in this Google, in this Minitab worksheet. So have you entered the data? After, please enter the data and tell me. Message me or tell me that you have entered the data. Okay, where is this message? Chat. Okay. How many of you are able to enter the data like this? Any doubt, please talk to me. If you are having doubts, please talk to me. In the beginning, go to this file, open worksheet. Go to file, open worksheet. Or okay, data entered. Now I'm going to process this data. Go to stat. The stat there is a stat menu. Go to stat menu. Go to regression, and this go to again regression. Go to this fit regression model. Okay. Start regression, fit regression model. Go to this, click this, fit regression model. Okay. You get this window box. So in this window box already force and length data is already there. It is captured in this window box.
Can you repeat once again?
Okay. So go to start regression, fit regression model. Is it available in your version? Statistics, start menu, regression, fit regression model. Are you able to get this option? Anybody have got this option? Okay, fine. So click this. So here you can see force and C1 force data, C2 length data is already available. In the responses, you have to click dependent variable. Response is for dependent variable. Response means Y. The variable Y is called response. It has many names. Y variable, response variable, output variable, dependent variable. All represent same variable. Different names used by different people. Okay, at different situations. So here you have to give Y or the dependent variable, which is length actually, because length is dependent on force. Force is not dependent on length. So Y is the response variable. In continuous predictor means X. X is called X variable, predictor variable, independent variable, input variable. All are same. Now somebody may be asking what is by continuous predictor variable. Continuous predictor variable means if your data is having some numerical value which is on a continuous scale. For example, in this length scale, your scale starts from 0 to infinity, right? Any variable, any value between 0 to infinity is a length scale. So it is a continuous scale, not a discontinuous scale. So those who have some idea about data analytics will know what is meant by continuous and categorical data. So here length is a continuous data. So length is taken as, if you double click length, it will come here. So sorry. If you double click force, it will come here. You have to double click force. So you will get here. You have to double click length to get here. So first ensure that you get length here and force here. Same way as I have done. If you double click force, you will get force. If you double click length, you will get length. So length should be in response, force should be in continuous predictor window. Length should be in the response window. Continuous force should be in continuous predictor window. Is it okay? Is this step okay? Are you able to do this step? Okay. Then go to model, don't do anything here. Go to option, don't do anything here. All by default, don't change anything here. Click OK. It is processing now. And the output is given. If you see the output, I am maximizing this window to see the output better. You go here. This is the session window. I have maximized the session window. In the session window, it is giving output of analysis of variance. That is analysis of that is a different analysis. Okay. Now I am not worried about this right now. I am not currently worried about this analysis of variance. Look at this model summary, and this is your model. What is this model? Length equal to 1.199 plus 0.4444 force. This is your regression equation. That is, this equation exactly explains the relationship between length and force. As we have seen here in our PPT, if you see in my PPT, what is the equation here? 1.2 plus 0.44 F. And look at this equation here. 1.199 So approximately 1.2. What is the difference between 1.199 and 1.2? Very 0.01 is the difference. So it is giving accurate value. Zero can be written as 1.12, and this is 0.044 force. So this is your regression equation. This is your model, regression model, or the model for explaining the relationship between force and length. Now you come here. This is the model summary. What is my model summary? This is the variance of the data. What is variance? S is the variance of X. What is variance? Variance of force. And what is this? R square value. 97.65 is the R square value. This is adjusted R square value, 97.18. This is predicted R square value. So this software gives three different R square value. Normal R square value, adjusted R square value, predicted R square value. I have explained about two R square value in my theory session, R square and adjusted R square. And I have told if it is a simple linear regression model, take R square value. And if it is multiple linear regression model, take adjusted R square value. Okay. So for this is a simple linear regression model. So we take R square value, which is 97.677, which is a very, very good R square value. That means your model is very close to the data. Okay. So very good representation. Now, what does this analysis of variance says? Analysis of variance says this is for the model, for the complete model. If p-value is great, if the p-value is less than 0.05, that means model is significant. That means model is having a very good significance. That is, model is significant. And for the force, if the p-value is less than 0.05, then this force regression variable is a significant variable which affect the output. So both are significant. So no need to worry much about this analysis of variance because all the p-values are less than 0.05. You come here, coefficients. For you can analyze the individual coefficients. How many coefficients are there? Two coefficients are there. This is the first coefficient, 1.199. So analysis of this coefficient is shown here. Look at the p-value. If p-value is less than 0.05, that is, the p-value gives the error of type 1 alpha, that is the percentage of type 1 alpha error. So it is a type 1 alpha, this is a probability of type 1 alpha error. If it is less than 0.05, it means the probability of type 1 error, that is less than 0.05, that is less than 5%. So in general, universally it is accepted. Probability of type 1 error should be less than 0.05. So p-value is less than 0.05. That means that this coefficient is a significant coefficient which represent the relationship. The next coefficient is force coefficient, which is 0.444, which is also significant because p-value is 0.044. Same thing we can do by manually also. We can solve this and get this coefficient and p-value, all these things. Also manually solve this analysis of variance, but there is no time. We need to have another 2-3 hours to, if you have to do explain and manually solve how this software is actually solving it and what is the meaning of each and every term in this table. That is coefficient, SC coefficient, t value, p value, how to find p value, how to find VF value. And this analysis of variance table, each and every term we can calculate separately and explain it. But that is not the scope of this presentation. Our scope of this presentation is how do you get a data model, a relationship between the factors without knowing anything about the model. So this is the model and this is the model summary. And this is analysis of variance output. This is analysis of the coefficient of the model output. So in analysis of variance, just look at the p-value. That means your model is significant, your force is significantly affecting output variable, which is length. Come to the coefficient table, your constant is significant, because constant p value is less than 0.05. Your force coefficient 0.0444 is also significant. So that is the output of this data. This is the output of this analysis of this data. Any doubts here, please ask me. If you have any doubt, please ask me. Let me explain the route before I go to the next data set. Any doubts here? It's a very simple data. This we can get it, this regression equation as well as this R square, you can get it in the Excel also. But this analysis of variance, this model summary, coefficient table, these things you won't get it in Excel. You have to use some statistical software. Okay, any doubts here? There is a doubt, I will explain it before going to next data set. Okay. Next data set, oxygen purity data, that is data set 2, that you can do analysis using the same method. In the first column, you type hydrocarbon level X. In the second column, you type purity Y. Then let me do it. Okay. Now I am changing this. I don't want to change this. I am adding C3, C4. I am adding hydrocarbon level X. Then C5 purity Y. Okay. Here I am writing 0.99, 90.01, 1.02, 89.05, 1.15, 91.43, 1.29, 93.74, 1.46, 96.73, 1.36, 94.45. Okay. 0.87, 87.59, 1.23, 91.77, 1.55, 99.42, 1.40, 93.65, 1.19, 93.54, 1.15, 92.52, 0.98, 90.56, 1.01, 89.54, 1.11, 89.85, 1.20, 90.39, 1.26, 93.41, 1.32, 93.41. Because instead of 1, I have entered a symbol. That's why it is showing. 1.43, 94.98. Last data is 0.95, 87.33. So 20 data is, you see here, column number 20. 20 data points are entered here. So I'm going to use the same statistic regression fit regression model. Instead of responses, I'm going to enter purity. Instead of force, I'm going to enter hydrocarbon level. So now click OK. Now analysis of regression analysis, purity versus hydrocarbon level. This is your equation. Purity Y equal to 79.09 plus 11.35 hydrocarbon level X. This is your regression equation. You check here, R square value is less 51. Adjusted R square value is 48 and predicted is 39. See here. So you get this R square value and regression equation. And here if you analyze the terms, constant term is significant because p value is 0.00, and hydrocarbon level term is also significant because 0.00 less than 0.05. So both the coefficients are significant. So this is the analysis of these two data set. Now come to data set 3. You can do data set 3 yourself. Okay, if you want, I can do simple data only. This is YX. Okay, X. Y is 28, 20, 25, 11, 17. 5, 3, 4, 1, 2. Right? Go to statistics, regression, fit regression model. Instead of the response, put to Y and was predicted with X. Analyze. So you get a very good equation which is called Y equal to 7.6 plus 4.2x. Look at the constant term. P value is less than 0.05. X term, P value less than 0.05. So both the terms are significant. So these three data set represent a simple linear regression model. Now I am going to data set 4, which is multiple linear regression model. Okay. So I am saving this data. Just for my future use, I am saving this data. How to save this data? You can save it anywhere you want. Okay. Piece. Now I'm going to enter the data set 4 in this worksheet now. First data is full strength Y. Okay. Second is wire length X1. You put X1 itself, that is enough. You put Y here, that is enough. Then put X2, that is enough. X2. X2, that is 9.95. 24.45, 31.75, 35, 25.00, 25.02, 16.86, 14.38, 9.60, 24.35, 27.50, 17.08, 37.00, 41.95, 11.66, 21.65, 17.85, 89, 60, 69, 10.30, 34.93, 46.59, 44.88, 54.12, 56.63, 22.13, 21.15. So 25 data. Now enter X1. X1 is 2, 8, 11, 10, 8, 4, 2, 2, 9, 8, 4, 11, 12, 2, 4, 4, 11, 12, 20, 1, 10, 15, 15, 16, 17, 6, 5. 50, 110, 120, 550, 295, 200, 375, 52, 100, 300, 412, 400, 500, 360, 205, 400, 600, 585, 540, 250, 290, 510, 590, 100, 400. Now I have entered the data. Now go to start regression, fit regression model. Instead of Y, press this responses as Y. Continuous predictor plus X1 and X2 both. The continuous predictor, you press X1 and X2 both. Okay, go to model. In this model, the terms in the model will be X1 and X2. Correct. So don't change anything in the model. Press OK. You get this results. So that is Y equal to 2.26 plus 2.71443 X1 plus 0.12253 X2. Okay. So here, this is the regression model. And this is the model summary. That is, this is variance of Y. This is R square value 98.11, which is very good R square value. Adjusted R square value is 97.94. Predicted R square value is 97.44. Analysis of the coefficients, constant term less than 0.05, just less than 0.05. So significant. X1 term, X1 coefficient significant, X2 coefficient significant. So all are significant. Okay. So this is a very good equation actually. Very good multiple linear regression. Suppose we find this coefficient, that is X2 coefficient is less, which can be eliminated because it's contributing very less. If you think like that, then do the same analysis with only X1 as the same analysis with only X1 as the continuous predictor. Press OK. You get this equation and R square value is 96 R square adjusted is 96.24. Earlier it was 97.94. Only small loss in the R square value around 1%. Otherwise, everything is okay. So this is a very good equation actually. So x2 you can eliminate depending upon the situation. If the situation demands, you can eliminate x2 from this equation and represent a simple equation with the x1 and y. Okay, this is about multiple linear regression model. Now come to polynomial model. Come to polynomial model. Now in this polynomial model, the data set 5 is, I'm going to use the data set 5. Okay. Put cost y, lot size x. Okay. Lot size x. So cost I am going to type it in this column 1.81, 1.70, 1.65, 1.55, 1.48, 1.40, 1.30, 1.26, 1.24, 1.21, 1.20, 1.18. Okay. This is 20, 25, 30, 35, 40, 50, 60, 65, 70, 75, 80, 90. Now go to the start regression, strict regression model. Remove this x1, y. Instead of responses, put cost y. Instead of continuous predicted, put lot size x. Now, this data, I am going to use a nonlinear regression model, polynomial model. So, you know, I want to introduce polynomial model. Go to this model. There is an option called the model here. In this model, you go here, you see only x term is there. So, I want to use x square term. So, how do you use x square term? Go to here, and terms through order 2. Select 2. Then click add. Now you get x square term here. This is x term. This is x square term. So in the model you have x term also, x square term also. Include constant in the model. Tick here. Okay. Okay. So press if you press OK, you get a nonlinear regression model y equal to 2.1983 minus 2.0.00222522 lot x plus 0.00125 x square you get. So that means this is a nonlinear regression model. Your R square value is 99.9. Adjust the R square value 99.53. Look at the coefficient analysis of a coefficient. Constant p value less than 0.05. X is less than 0.05. X square is also less than 0.05. So very good polynomial regression model with the quadratic term. One linear term, one quadratic term. So both terms are there. So very good model. Okay, this is how we do this. So where is the option here to introduce the nonlinear quadratic model? Go to the model here. In terms through order, you select 2 and press add. Then you will get the quadratic term. If you click 3 and press add, you will get x cube term. Now x cube term is not required. We are going to get satisfied with the x square term also. Suppose you want to see out of curiosity what will happen if x cube term is added. So what you can do is go to model here, go to 3 here, add this x cube term. This is x cube term I have added. Now you press OK. So you see here x cube term is added here. So this is the equation y equal to 2.252 minus 0.02 x plus 0.0001 x square plus 0.000000 x cube. Now analyze the constant, analyze the coefficient. Constant is less than 0.05 p value, so significant. X is significant. X square also significant. X cube is not significant. X cube is not significant because p value is greater than 0.05. So you can eliminate x cube term and be satisfied with this equation, which is actually with the quadratic term itself. You can be happy with this. Very good. You can see here in the x cube, if when I introduce x cube, r square x cube, r square is 99.51, 99.69 actually. Here r square is 99.69. R square didn't change by introducing x cube value. R square didn't change. So based upon this coefficient analysis, this p value is less than greater than 0.05. So you can eliminate this x cube term. So that is about this two data sets. Now I'm going to proceed to next laser drilling data. Laser drilling data set 6. Let's save this current worksheet as okay. So I'm going to close this and I'm going to delete all these things. Okay. Now I'm going to go to this laser drilling data 6, data set 6. Okay. So what is data set 6? Data set 6 is actually laser drilling data, and data is given here. So what I am going to do is I am going to copy from the Word file. I am going to copy it to this Excel. This is this worksheet. So I have just copied. You see here, I have just copied this. What is done here is this is x1, this is x2, this is x3, this is y1, y, this is y. So there are y is taken 2 times, data is taken 2 times for each setting. So instead of the table is having only 15 setting. So I am considering it as 30 data points because RA value is the output variable or response variable. It is taken 2 times. So how many data sets are there? 30 data sets are there. So I am going to introduce 30 data set from this table. So you see here in my worksheet, there are 30 data sets are there. With the same setting, x1 2.7, x2 1, x3 500, you enter 2 times this data RA value. You enter 2 times the same setting. In the first data 1.3 you write, second data 1.5 you write. So similarly, you write all the 15 data set, you get 30 data points. So now I am going to analyze this 30 data points. I should get an equation for RA in terms of, I am converting this response into RA in terms of x1, x2 and x3. x1 is power, x2 is scanning speed, x3 is number of passes. So go to statistics, DOE, regression, statistics, regression, fit regression model. Here in the response, double click RA, in the continuous predictor, double x1, x2 and x3. Okay. Now you see here, you are getting a simple equation here. Okay, only a multiple linear regression equation is there. I am not satisfied with this multiple linear regression. I want quadratic as well as interaction term. So how to introduce quadratic and interaction term? Go to here, go to model, make it 2 here. Interaction through order 2, terms through order 2. Add. Select all the terms. Add. Click add. You get 3 interaction terms added. If you click the next add, you get all the 3 quadratic effect added. Click OK and click OK. You get an equation. This is the equation RA equal to 1.854. The exact same equation which I have mentioned it in the data set. So it's a complex equation, right? It has a linear effect, quadratic effect, an interaction effect. Interaction effect is actually interaction effect is a nonlinear effect. Quadratic effect is also nonlinear effect. Look at the adjusted R square value 89.40. So very good adjusted R square value. So we can be satisfied with this adjusted R square value. Similarly, you can do it for waviness data. I have done for roughness data, RA value data. Another data set 7 is there. Similarly, we can do for I am just deleting this data set. I'm going to copy it instead of RA, I'm converting into WA. I'm going to copy the data set 7 into this data set 7. Okay, I'm going to copy data set 7 here because since the WA is taken 2 times, I have copied the settings 2 times. So total 30 data points are there. Then I am finding out WA value. Copy the WA value and paste it here in this column. Then copy the second column of WA value, paste it here. Okay, now 30 data points are there from data set 7. So go here, statistics, regression, simple regression model. Instead of RA, put a WA, responses WA, continuous predictor X1, X2, X2. Go to the model. I need all these terms X1 square, X2 square, X3 square, X1, X2, X1, X3, X1, X2, all are there. Okay. Click OK. You get an equation like this. This is a multiple nonlinear regression equation. And R square adjusted value is 87.48, which is a very good R square adjusted value. And you can check the coefficients, analysis of the coefficients. Constant term is significant. X1 term is not significant. Sorry, significant, less than 0.05. X2 is significant, X3 is significant, X1 square is not significant. X2 square is significant, X3 square is significant, X1, X2 is significant, X2 all are significant except X1 square. So since X1 square is not significant, what is the X1 square term? You see here X1 square 172.2 X1, X2. X1, X1, that is X1 square is not significant. So you can eliminate in the next analysis, that is statistics, regression, fit regression model. Go to this model here. Since X1 is insignificant, remove this X1. Click OK. Click OK. Now you see here, all terms are significant except X3 cube. So remove X3 cube again. The next analysis that I am actually refining the model now. Go here, X3 cube, remove it. Okay, that's okay. Now this is a simplified model. All terms are significant, and your R square adjusted value is 84.63, which is not bad, but a simple model is there. So you can have a complex model like this. You can have a complex model like this, or by eliminating 2 insignificant terms, you can have a simple model like this. So it's up to you. You have to decide how many terms you need to have in the model, depending upon the R square value and also the cost of the data point that you are measuring, as well as the, you will understand, right? Here, x1, x2 is not, x1 square, x2 square, x3 square is not going to increase your, because it is actually x1 square and x3 square, the square of x1, x3. So it is not going to increase your cost of the experiment. So you can include it, include all the data points and get a complete model with all the interaction effect as well as quadratic effect and linear effect. You get this model. So that is the end of this workshop. If you have any specific doubts, please ask me. I can explain you any specific doubt if you have. If you want to ask some anything specific about how to get the data, develop a data, or how to generate the data, how to do the experiment. If you have any specific questions, you please ask me. Sir? Mansur sir? Participants, any doubts?
So, no doubt, sir. And it's a wonderful session, sir. Thank you, sir.
Okay. So participant can interact with me, or if they have any specific questions or doubts in their minds, can be discussed now. Because
So it's okay, sir.
okay, sir.
Okay. For vote of thanks, I'm inviting Mukhtar Ali.
I would like to take this moment to offer heartfelt gratitude towards Dr. Mubarak Ali sir for this wonderful session. The session was informative as well as interesting. We were able to understand the types of modeling extremely thanks to the integration of problems too was helpful. The hands-on session through Minitab also was really interesting. How you navigated us through these complex topics in such a simple way was an art of its own. Thank you, sir, for sharing our time and thought with us. This is a small token of our gratitude as we share you a virtual moment. Share screen. Screen share on.
Thank you very much, sir.
Thank you, sir.
Thank you for giving this opportunity to share some of my understanding about this data-driven model. Thank you very much for this, and I congratulate all the team members, the coordinators of this FDP, and wish you grand success of this FDP.
Thank you, sir. Thank you, sir.
Thank you. Thank you.
I thank all participants for taking this time to be a part of this session. We'll end the wind up for now. We'll start the session at 1:30.
So today's afternoon session is handled by Dr. Shihabuddin KV, Assistant Professor, NIT Calicut.